Okay, so hopefully everybody had a good weekend. So we were gonna finish up chapter 11 today. So I really only had a couple things to say left about chapter 11 before getting into chapter 12. One warning I'll give for chapter 12 is that if you're going through chapter 12 in the textbook, the early bits of chapter 12 are a lot of formal stuff that we're going to go over in like, 5 minutes or so. So our actual, like, the meat of chapter 12 is not until later. And so we will get to the meat of chapter 12 very, very quickly because I'm not interested in taking you all through all of the more formal aspects of that material. So you'll quickly see what I mean if you just have a look at that stuff and compare to kind of how we're going to treat it. And so, anyway, I wanted to do one example, as I promised from last time, of finding the line of intersection for two planes. And then after that, I'll write out the formula for computing the distance from point to a plane, and then we will move on to chapter 12. We're allowed to use calculators in this class. So you can use calculators to, obviously, to check your work on exam homework and all of that. But the thing is that if something isn't graded, if something isn't on the paper, then it can't be graded. So if you want credit for something, you'd better put it on the paper. What sections of the formal material? Let me look at the textbook real quick to remind myself. So 12.1. 12.1 is like the definitions and some examples. So, I'm going to offer these same examples. So technically, I'm going to do all of this. Like I will. Okay, so 12.1 I will cover. So it is not one of the things that's going to be tossed aside. 12.2, again, I will cover all this stuff. It's just that I'm not going to I'm not going to even write down the definition of limits of vector valued functions, continuity of vector valued functions. I'm going to tidy up all of that stuff in one go. So a lot of the things that show up in boxes in 12.2, I will go over very quickly. So 12.2 will mostly be skipped. 12.3 will mostly be skipped. So 12.2 and 12.3, I will cover that material, but very, very quickly. In fact, from both those sections, the main thing I will cover is corollary 12.11, which is on page 768. You don't have to worry about writing that down or anything. I will mention all of that stuff when we get to it. And so really, the meat of chapter 12 starts in 12.4. So 12.4 is really where the meat of chapter 12 starts, and we will quickly get there. So essentially, I will start with that stuff on Wednesday. So anyway, for the time being, the last couple things I wanted to say about planes, I wanted to do this nice example of finding the line of intersection for two planes that are not parallel. So, of course, I could frame this question in a number of ways. So let's consider planes script P1 and script P sub 2 described by equations. So described by the equations. Let's say x minus 2y plus 4z is equal to 1, and 2x plus y minus 4z is equal to minus 1, okay, respectively. And so you'll see it written like this. So the equation for p sub 1 is this first one, and the equation for p sub 2 is this second one. Okay, so here's two equations that describe these planes. So then show that these intersect. Show that these planes intersect and find equations for the line L. So find, let's say, parametric equations. Find parametric equations for the line L of intersection. Okay. These types of problems involving planes are really, really nice because they kind of test a bunch of things at once here. Okay, so a lot of things are being mentioned here. Can we just write out the equation and say entered into calculator? No. No, you gotta do it. You gotta do it if you want credit for it. Okay, so what do I do here? We mentioned last time if you have two planes in space and, well, they're either parallel, meaning they don't intersect, or they're not, right? So they do intersect. And if they intersect in a line. Now, we also saw last time that a way to tell whether or not two planes were parallel was whether or not their normal vectors were parallel. So we could actually look here and think, are their normal vectors parallel? Okay, that is, are they scalar multiples of each other? And you can just look here and see, so the normal vector here, or a choice of normal vector for p sub 1 is 1 minus 2, 4. Choice of normal vector for p sub 2 is 2, 1 minus 4. Just looking at this slot, the only possibility here would be that they're related by a negative, right? Because this entry is 4 and this entry is minus 4. But that's not the case in the other two slots. So these things actually do intersect. So I could show that these things intersect just by writing my normals, right? I could write my normal vector to plane p sub 1 as 1i minus 2j plus 4k, and my second normal is 2i plus j minus 4k. So there's those two vectors. Those things are clearly not parallel because they're not scalar multiples of each other. And so I automatically know that these things intersect straight from that, okay? So these intersect. Okay, so note N1 and N2 are not parallel. Thus, the planes P1 and P2 are not parallel. Okay. i.e. they intersect, okay? And so now we know they intersect. In this case, though, I want to find the line L of intersection. So geometrically, now I want you to think. This can be a little hard to think out, so imagine, and from this angle, it's hard for me to show you what's going on here. But if you have two planes in space, let's say here's one plane, and maybe it looks like this, right, this sheet. And then I have another plane that intersects this first plane. Okay. And here is the piece of their line of intersection. Right? So if I draw the whole line, it looks like this. So here's the L that I'm seeking. Okay. And so in this picture here, this can be a little confusing, and that's not the greatest picture. But I have a normal vector. If this is script P1 and this is script P2, then I have a normal vector N1 that is normal to P, right? And then another one that is normal, so this is N1. And then another one that is normal to my other plane. Okay. What do I need in order to write the equation for this line L of intersection? Well, I need a point that is on this line, right? And so where's that going to come from this info? From this info, I have equations describing two planes. A point on this line L of intersection is going to be a point that is contained in both of the planes. So it's just going to be a point that is a simultaneous solution to these two equations and three unknowns. Okay. All right, so that's how I find my point. How do I find my vector L? Right? Any vector that is parallel to this line will work. What's going to work here? So this is where it might be hard for you to grasp exactly what is going on here because this picture is not the greatest. But what's going on here is I'm seeking a vector that is parallel to this line. How do I get it? Well, if these two vectors, when I cross them, I get a non-zero vector, this vector that I obtained from crossing those two vectors is in fact parallel to the line of intersection, right? How can that be? I have two planes that intersect, right? So since they intersect, the cross product of these two vectors is not going to be the zero vector, right? Since they're not parallel. Okay, and so that vector, right, which is going to be perpendicular to both of those normal vectors, is necessarily parallel to the line of intersection. Okay, so note, so to write out L, we need a point on L, that is a point on both P1 and P2. So we need a point that belongs to both, and a vector parallel to my line L, and we're calling that vector big L. And this vector is going to be the cross product of those two normal vectors. Okay. All right. And so let's go ahead and cross these two vectors. Now, at this point, something about crossing these two vectors is actually checking our work a little bit, because this cross product definitely shouldn't be the zero vector if these two planes actually intersect. And so, computing my cross product, top row is ijk, middle row is n sub 1, which is 1 minus 2, 4. Bottom row is n sub 2, which is 2, 1 minus 4. So computing this cross product really quickly, I have something times I, where that something is 8 minus 4. Okay, minus something times j, that something is minus 4 minus 8. All right, plus something times k, and that something is 1 minus minus 4. Okay, I think that's right. So this is 4i minus minus 12, so plus 12j. 1 minus minus 4, so that's 5, so plus 5. Okay, all right, so there's my vector. That's not the zero vector, so more confirmation, right, even though we didn't need it, that these two vectors actually intersect. Okay, so here's the vector that is parallel to L. Now all I need to do is find a point that belongs to both planes. So now all I need is a point common to both planes. Well, what are those equations? So the equation for the first plane is x minus 2y plus 4z is equal to 1. For the second plane, it was 2x plus y minus 4z is equal to minus 1. Okay. And so there's a number of ways, and there's obviously a number of points that we could come up with here. So the question is, how do you want to do this? Well, all we need is to find a point that satisfies both of these equations. Okay, so what's something we could do? We could add these equations. If we add these equations, and why would I think to do that, right? Why would I think to add these equations? Well, I have 4z here and minus 4z here, so I'm going to get rid of the choice in z here, and I'm going to get some equation in two variables, x and y. That's something I could do. Of course, I could also just fix z, right? I don't have to add these. I could fix z to be something and solve the resulting equation. So there's a number of things I could do here. I'm going to add both of these, and what I get is 3x minus y is equal to 0, right? So adding both of those equations, I do that right. 3x, yes, minus y, yep, those cancel. And I get 3x minus y is equal to 0 here. So then here I get 3x is equal to y, so I have a choice that I can make. If x is equal to 1, then y is equal to 3. And then whatever choice of z I make should work in both cases, right? So what do I mean by that? Well, so my choice of z here, what am I going to do? So if I go and plug this into my first equation here, I get 1 minus 2 times 3 plus 4z is equal to 1. And so what I get is 1 minus 6 plus 4z is equal to 1. And so subtracting 1 from both sides, adding 6, I get 4z is equal to 6, or z is equal to 6 over 4, 3/2. Right. So now, this for sure belongs to the first plane. I don't have to check it. But does this point belong to the second plane, right? We're just doing this to check that this actually works. And so this would be 2 times 1 plus y is 3 here, minus 4 times 3/2. What is that? This is 2 plus 3. Minus 4 times 3/2 is minus 6. Well, that is 5 minus 6, which is minus 1. Hey, that's exactly right. Okay. Now, again, do you have to check this? No, right? You can, like, if you do this algebra, you understand that this is what is going on. I'm just doing this for you all. So we have a point that belongs to both planes and a vector that's parallel to it. So I said I wanted parametric equations. So my equations for L are going to be x equals 1 plus 4t, y equals 3 plus 12t, and z is equal to 3/2 plus 5t. Right? And t is just some real parameter. Okay. All right. So questions about that. If you have them, you can post them in the chat, and I'll have a look at them here in a second. Okay, so one more thing I wanted to mention about planes, and then we will be done with chapter 11. Okay, so, oh, let me get some more paper. That's gonna not feel the best to write on. So, similarly to this thing that I did for lines, right, computing the distance from point not on line to a line, I want to compute the distance from a point to a plane. Okay, so let P be a plane with normal N. Okay, and let P sub 1 be a point not on this plane. Then the distance from P1 to P is d, or we write it as distance from P1 to the plane P. This is the absolute value of n dotted with the vector P0, P1, divided by the length of n. So compare this with the distance formula for the distance from a point to a line. Of course, what is this P0? Where P0 is any point on the plane. Okay. And so in some ways, computing the distance from a point to a plane is actually more convenient than computing the distance from point to a line, because rather than having to do a cross product, I actually just do a dot product. Right, with my normal vector playing the role of my vector L from what we did for lines. Okay. And so looking at the chat here. I'm confused on how you found Z. And yeah, so as was pointed out, I basically what I did there is I added the equations. Okay, I added the equations to get a simpler equation involving just two variables, and then I just chose values. I just chose like x equals 1. Okay, I just chose a value there. And once I chose that value, then it determined y and z. Now, I didn't have to do it that way. You could have started with those two equations and chose a value for z or chose a value for y to eliminate that variable. Now, why can you do that? Well, you have two equations and three unknowns. Okay, and so in order to get a solution, you're going to have to nail down one of those things. Okay, you're going to have to fix one of those things. Otherwise, you're not going to be able to come up with a solution to that. But the nice thing is that you can fix one of those things to be whatever you want. Okay, and that determines the values of the other two parameters. Okay, so you can practice with those. You'll be doing some of that in your discussion this week as well. Okay. So it is the absolute value. It's not the length because this isn't a vector, right? This is a scalar valued thing. So I have two vectors that dot them together. That's a scalar, but the dot product can be whatever. The dot product can be any number, and so I take the absolute value for this to make sense as a distance. Okay, so that is absolute value because that thing within those bars is a scalar. Okay. All right, so that's it for chapter 11. So now chapter 12 stuff. And once we get to the meat of chapter 12 stuff, I wish we had a ton of time to spend just on curves in space, because that alone, if you find yourself interested concerning the topic of curves in the plane or curves in space, then you should take Math 436, because it is an entire course dedicated to curves in space. So I highly recommend. It's one of my favorite courses to teach because it's an entire semester of very, very, very interesting stuff concerning curves and surfaces in space and in the plane. So yeah, it's there's a lot of stuff here, a lot of very nice topics, and a lot of really, really awesome examples that unfortunately, like I said, there's more cool stuff to cover than I can even get into. So I will try to touch on all the cool stuff I can, but unfortunately, we don't have time to spend weeks on it or anything. And I don't know, maybe you all wouldn't find it as thrilling as I do, but I think you would. I have high hopes that you would, because I think some of the stuff about curves in space is so interesting that I feel like almost anybody would enjoy it. So anyway, okay. So before I can talk about curves in space, which is really the thing that I'm interested in, from coming from this chapter, before I can talk about that stuff, though, I have to set up the terminology and the notation behind curves in space and this description. And you'll see that by the time I'm ready to write it out, we've already seen an example of it. Okay, and so what I want to talk about first are vector valued functions. Vector valued functions, or VVFs. Okay, as I will abbreviate them for the rest of the course. Okay, what is a vector valued function? The obvious description is it is a function that is vector valued, right? And I'm not really just saying that. That is exactly what it is. Typically in Calc 1 world, right? So you have a function f that takes x, which is a point, right? X is a real number. Okay, it's a single real number, and it assigns to it f of x, which is also a real number. Okay. Now in Calc 3, we're going to do some different things here. We are going to take in single real numbers and produce things that are not real numbers. And we're also going to take in vectors and produce real numbers. Okay. So in Calc 3, we're going to do two different things. So the first thing that we'll discuss is we are going to take real number, say t, and we are going to assign to that real number a vector, f of t. So this is a real number, this is a vector. So this is real number, and we assign to it a vector. So that vector could be in R2, could be in R3. It could, of course, be in higher dimensional spaces, but for us, we're just going to stick to R2 and R3. Okay. And so this function, big F, that assigns to each real number in its domain a vector is called a vector-valued function. So this is going to be the first thing that we do in Calc 3 that's different from what we did in Calc 1 and Calc 2. The other thing that is going to be the topic of Chapter 13 and 14, and really, well, the rest of the course, is the following. It is we take in a vector. So we start out with a vector, or we're going to write it as an ordered pair, x, y, and then we assign to that ordered pair a real number, f of x, y. Okay, and so if we're using more advanced math notation, how would we write this? So here we would have, this is something in R2, not in R1. This is a vector. And this f of xy is actually in R. It is real valued, right? So this is a real valued function of two variables. This is going to be what we spend most of the course talking about. Okay. So if we're using this, if we're writing this using fancy math notation, in Calc 1 world, we have real valued functions of a single variable going from R to R, right? Now, of course, not every function is defined on all of R, so it's defined on some domain that goes and it maps to R, and this domain would be a subset of R. Okay. All right. So these would be maps from, in the case of a vector valued function, it takes in a real number and it spits out a vector either in R2 or R3. So real number in, vector out. The thing that we'll talk about later takes in, say, a vector. And of course, we're also going to talk about functions of three variables, so maybe it takes in a triple of real numbers, and it spits out a real number. Okay. All right, so that's kind of the conceptual idea of what's going on here. So then what is a vector valued function? A vector valued function is just a function that takes in a real number and spits out a vector, right? So quick definition, a VVF, that is vector valued function, is a rule F that assigns to each real number in its domain that we'll call D, right? So it's a rule F that assigns to each real number in its domain D a vector in R2 or R3. So some vector. We call that vector f of t, right? If we're saying that the real number in question is t, this vector is called f of t. Okay, so let's just have some examples here. So now, I defined this in a very vague way, but you all already know that when it comes to functions, could I be like very vague and hand wavy and say, consider the function that takes a number and doubles it and then subtracts 15? Of course, I could say that, but we have algebra, so we have much more convenient ways of writing that. So I can describe these rules by simple algebra here, right? So consider the vector valued function that looks like this. Let's say f of t is a vector valued function defined in this way. Of course, I could write this in a different way, right? I could write this as 5 minus 2ti plus t squared plus 2j plus 37k. Right? That's another way of writing it. Okay. And so what does this function do? What does it tell you? Well, I don't know. I'm just looking at it, right? It's just an algebraic rule for assigning real numbers vectors. So, for instance, to the real number 0, what vector gets assigned in space? Well, 5 minus 2 times 0, 0 squared plus 2, and 37. So this is the vector 5, 2, 37. Right. Okay. The vector that this function assigns to the real number minus 1 is, we can do this in our head, 5 minus 2 times minus 1, so that's 5 minus minus 2, so that's 7. Minus 1 squared plus 2 is 3. And 37 doesn't even depend on t. And so the vector that this vector valued function assigns to the real number minus 1 is 7, 3, 37. Okay. Okay. Let's do another example. How about let's do ti plus square root of tj. Okay. So the first thing that you note is that this vector valued function is not defined for all real numbers t. Okay, so in fact there's restrictions here. What restrictions do I have here? Well, are there any restrictions in the first slot? Right, is there any problem plugging in t being equal to anything? Well, no, right? So there's no issue coming from this slot. Are there any issues coming from this second slot? Well, t can't be negative, right? And so no restrictions here. T can't be negative here, right? And so t needs to be non-negative. So t needs to be greater than or equal to 0. And so my domain D is the set of t such that t is greater than or equal to 0, right? All right. Now, some of you might have actually noticed that this vector valued function, if I write it not using ij notation, if I write it in coordinate notation, it looks like this. Okay. What is that? So what is that? So of course, this is a part, right, of, yeah, this is, so you'll notice, right, that this is square root of t, right? This is the graph of square root of t, but not, this is actually so parametrically I can describe square root of t, of course, in a way that allows me to graph it like this, right? And so it's not simply the graph of square root of t. Okay, it is this parametrized version of square root of t. Okay, and I'll talk about this in a second. So I'm jumping ahead of myself talking about parametric curves and why we can do this without it failing to be a function. Okay, because this vector valued function, the only requirement, right, here is that this assignment is done in a way that's not ambiguous. Okay, and so we can parametrize curves using another parameter, say t, to parametrize the x, y, and z slots, that allows me to define graphs of curves that, of course, I can't graph if I'm just thinking about them as the graph of a function, because this curve is, for instance, not the graph of a function, right? It fails the vertical line test. But it doesn't matter. It's a really nice curve. Okay, so basically, if I want to talk about curves that pass over and under themselves, then they're going to fail a vertical line test, but I don't care. Right? I don't care that they're going to fail the vertical line test. I still want to talk about them. And I still want to do calculus on them. And so this is where the parametric idea gives us a lot of power, because you can't do this, right, without it. Okay, so you see where this is going. So one more example here. So you note, right, that in general, if I have a vector valued function, what is it actually? It is just a vector of real valued functions. Okay. So where each f sub I of t is a real valued function. Okay. So this is what my vector valued function looks like. Of course, written in another way, the reason I'm stressing both ways is because you're going to see them. You're going to see both of these things used over and over and over again. So there's the other way they're written. Okay. So what is it that's being said here? This is the important fact. A vector valued function is just a vector containing real valued functions. Why is this important? Because this statement, right, recognizing this allows me to, you know how at the beginning of the lecture I said that I planned on quickly kind of brushing aside a lot of the formal stuff at the beginning of chapter 12. This statement alone is what allows me to do it, okay? And the reason why this statement allows me to do it is because all of that formality is basically just taking advantage of this over and over and over again. Okay, and so to spoil the fun a little bit, the way that it's doing that is, now I've defined this new object, a vector valued function. Okay, so I've defined this vector valued function in a way that it is made up of real valued functions. Now, I had a bunch of stuff, right, from in Calc 1 and Calc 2 that I did to real valued functions. So, for instance, taking derivatives, taking, of course, before that, taking limits, right? And so, what do you think is going to be the definition of this, right? Oh, I used x. Yeah, okay. I'm going to forget that. I'm going to use t. Okay. So, what do you think this is going to be? What do you think the definition of the limit is going to be? Well, it's going to be the limit applied to each of the component functions. Okay, it is going to be limit. So it is the vector valued, or it is the vector consisting of the limits of each of these components. So it would be this. Okay. And so, basically, any kind of analysis stuff, any kind of calculus stuff that you want to do to a vector valued function, you just do it to the components. And so, what does this statement say? That the limit of a vector valued function is the vector containing the limits of the components of that vector valued function, which are real valued functions. So this concept, I'm like, what is this, right? Limit of vector valued function, I don't know. But this, right? So I'm sad because I don't know. But these are limits of real valued functions, right? Which I know. I'm very happy. Right? Because I know what these are. I know how to take limits of real valued functions. Okay. And so that's the story with vector valued functions. And you can swap the words. So we are going to talk about derivatives of vector valued functions. What do you think the derivative of a vector valued function is going to be? It's going to be the vector valued function containing the derivatives of the components of the vector valued function you started with. Okay. Similarly, we're going to talk about taking an integral of a vector valued function. This is something that doesn't come up as much. And it's going to just be the integral of the components. Right? And so, for instance, we can apply this to derivatives. Let's take derivatives here. What is the derivative of a vector valued function? What do you think it's going to be? Oh, it's going to be the vector valued function I get when I take the derivative of each of the components. Oh, that's not where the 3 goes. What about the integral, right? Let's take a definite integral of a vector valued function. What is that going to be? It's going to be exactly what you think. It's going to be the constant vector you get by integrating each of the components. Okay. We're not going to do this very much. We are, however, going to take many, many derivatives of vector valued functions. So this we're going to do quite often. Okay. Yes, there's a pattern, exactly. So rather than beat you over the head with this pattern, it's obvious that you all recognize what's going on here. And so I can subsume all of that by just saying it's a vector containing real valued functions. And basically anything you want to do to a VVF that you could do to a real valued function, you can by just doing it to the components. And when I say just doing it to the components, what I mean is that you form the vector made up of the components that have been changed in that way. So you want to take a limit of a vector valued function. You form the vector that is made up of components where you've taken the limit of each of the component functions. Okay. Can you take an indefinite integral? Absolutely. Yeah, you can. And it's fine. Yeah, taking indefinite integrals is fine. You can definitely do that. Yeah, in fact, you would get, instead of getting a single constant of integration, you would get a constant vector of integration. So you would get a vector containing constants of integration in that case. So yeah, so Brandon asked this question in chat of whether or not you could use indefinite integral, or whether you could take the indefinite integral of a vector valued function. Absolutely. Yep. Definitely can. Okay. What this also tells you is that any property relies, so what this also says, and maybe this is important here, any property we want a VVF to have comes from the components. That's maybe not the best statement. What do I want to say here? What am I really trying to say? What I'm trying to say is, for instance, let's say we want to ask the question, is a vector valued function continuous? So continuous at, say, t naught. Okay. Well, what does that even mean, right? We would have to come up with a definition of continuity, which is done in the textbook, and that's exactly the thing I was going to tell you. I told you I was going to skip. You can come up with an epsilon delta definition of continuity for vector valued functions. But what we're going to do is just say we're going to define continuity to be the thing that is inherited from the components where we know the components are continuous at t naught. And so the way we say this is that we say that f of t is continuous at t naught if and only if each of its components, say f sub 1 of t, f sub 2 of t, and f sub 3 of t, are continuous at t naught. Okay, and so this is the definition of continuity. This is also similarly going to be the thing that we do for differentiability of vector valued functions. Okay. And so if its component functions are continuous at a point, then the vector valued function itself we say is continuous at t naught. Okay, and the key factor here is that we know what continuity of a real valued function means. We know what differentiability of a real valued function means. Okay, and so similarly, we say f of t is differentiable at t naught if and only if each f sub I of t is differentiable at t naught. Okay. Okay. So this is what I meant when I said any property that we want a vector valued function to have, or any property that we're interested in a vector valued function having, or being able to describe whether or not it has it. We just look at the components and we say that it has this property if the components do. All right, all of the components do. Okay, similarly, here's one last thing that's kind of an edge case. This is something that's not going to come up very frequently in this course either, but just to see it. Say you have a vector valued function that looks like this. Okay, so we'll say t squared plus 1 times I minus, say, square root of t plus 1 j plus 1 over square root of, say, t plus 1 k. All right. Okay. So what is the domain? What is the maximal domain of f here? All right, how would you figure that out? Well, you would look at the maximal domains of each of these functions, right? And then what would you do? In the language of set theory, you would intersect them, okay? In normal speak, we're just going to look for what they have in common, right? And so what's the domain of t squared plus 1? Or rather, another way of looking at it, just like I did before, what restrictions are being placed on you by having t squared plus 1 here? Well, nothing, right? T squared plus 1, I can plug any value t into that, and there's no issues, okay? What about square root of t plus 1? What issues do I have, right? Well, square root of t plus 1, I mean, I'm taking the square root of t plus 1. T plus 1 can't be negative then, right? And so t plus 1 needs to be greater than or equal to 0, and so t needs to be greater than or equal to minus 1. That's what I get from this component. Okay, from this component I had no restriction, so I was good. From this component I got this restriction that t must be greater than or equal to minus 1. But I have to look at the last component, right? And looking at the last component, t being equal to minus 1 is no good here, right? Because when t is equal to minus 1, this is square root of 0. That's fine in this slot, but it's not fine in this slot where that's in a denominator. So from this, I get that t must be greater than minus 1. And so what I do is I look at all of these and I look at what they have in common, and the biggest possible domain I could form from these three restrictions. So here's no restriction. This requires that t be greater than or equal to minus 1. This is fine with all of those except t being equal to minus 1, and so this is our biggest possible domain. So the maximum possible domain is the set of all t such that t is strictly bigger than minus 1. Okay, so again, even notions about which, yeah, so people have put it in chat in interval form. It's open interval minus 1 to infinity. Yep, so this is minus 1 to infinity. So this is another example showing that exact same idea, right? That the vector valued function being made up of real valued functions, all of its properties that we want to talk about come from the properties of those real valued functions. So if you want to understand what's going on, you pass to the real valued functions. Now, that's true for all of this formal stuff that we're building up. But as you'll see, this is not something we can rely on forever, and there really is new stuff that comes up here, and we'll see that on Wednesday. So on Wednesday, first thing, I will start with basically the meat of Chapter 12, which is using these things for what we really want to talk about, which is curves. Okay, as you might have already noticed, there's an easy example of vector valued functions displaying a curve in space, so we'll talk about that next time. So anyway, you have homework that is due late on Wednesday, so if you have any questions about that, you can ask them before lecture on Wednesday. Ask them in the chat if you have any lingering questions, since, like I said, it's not due till midnight on Wednesday, I think. If I correctly made that due date, then yeah, it's not due until midnight on Wednesday, so you still got plenty of time. Anyway, just let me know if you have questions. I'll see you all on Wednesday, where we'll start on 12.3, I think is the section, or actually 12.4 is where we'll start on. What is the symbol with two dots, and that means defined to be. So if you see me writing, like if I write A colon equals, A squared minus 2B, okay, What this means is that big A is defined to be stuff. Now, the reason why you would use this symbol is that if I'm doing a bunch of computations, this tells you that this line didn't come from some magic computation I did in my head and put on the paper. So when you see this, it means you're not missing something that went on before. It's that this big A is defined to be this quantity, so it's not coming from some computation you didn't see. Okay, so that's what that symbol means. Anyway, I will see you all on Wednesday.